So today I'm going to tell you a little bit about our efforts, recent efforts to explore phases of matter in trapped ion crystals in Chris Monroe's trapped ion group. And here what you can see is an illustration of one of our systems where we have a 27 ion chain. Each of these blue spheres is an individual atom that we can trap and isolate completely from the environment. You can see here the electrodes that we use to trap those ions. And we can use the spin degree of freedom for these ions and program their interactions using this array of tightly focused laser beam. And today I'm going to tell you a little bit more about these type of quantum simulators, how they work, and how can we exactly program their interactions. I'm going to tell you in more depth how we can use these simulators to study different models, how we can study continuous symmetry breaking in a one-dimensional system with long-range interactions, how we can go beyond the ground state and study and probe some finite energy properties of different systems or phase transitions, and also share some preliminary results that we have with signatures of topological edge states that we can observe in one dimension, and also some dynamics of string breaking. So let me start with how trapped ion quantum simulators work. So what you see here is a fluorescence image of our 27 ion chain that is made of atomic ions. Each of these is an individual ytterbium-171 atoms, and we like atoms because they are identical. So whenever we scale up the system, they always maintain the same properties. And specifically, this atom has a very simple energy level. It resembles much that of the hydrogen. We take a pair of spin levels and we denote them up and down between two different hyperfines, and they feature quite long coherence time. In our system, it's about 1 second long. And we can also very efficiently prepare the state to be either up or down, and also detect what the state is just by shining some light that is resonant with some excited state transition. And we would see an ion only if this state is up, and otherwise it would be dark. Now, the way that we form these crystals is that we assemble them atom by atom. We apply trapping forces and also laser cooling. Here you can see how we assemble those crystals. We have a shared mutual common harmonic potential, and we can control the dimensionality of this crystal by applying a weaker confining force along one dimension, and therefore the crystal prefers to crystallize along this direction. And of course, after cooling it out near the ground state, then all the ions are near their equilibrium position. Now, still at this point, the Coulomb interactions are very important because they dominate the collective motion of the ions. And one way to look into this is that we can poke one of these ions and push it a little bit away from equilibrium. And because of the Coulomb interaction that is long range, that would cause all the ions to participate in the motion. We would have a set of collective modes of motion. It's just a linear system. We can think of the ions as masses that are connected by known local springs. Now, quite importantly, because the ion's motion is isolated from the environment, and this is a quantum motion, therefore we can consider each of these modes of motion as quantum harmonic oscillators, whose excitations are phonons, or just vibrations of the crystal. And therefore, whenever we look at this system, we always think of it as a chain of spin, and also a chain of bosonic modes that we have here. Now, at this point, we still have no spin model, because the Coulomb interaction, although it's long range, it does not couple the different spins. It's independent of the spin. It depends only on the charge of the ions. So in order to engineer some spin model or some spin Hamiltonian, what we do is that we introduce some laser beams, have some amplitude and frequency, and they realize this relatively simple Hamiltonian. We have just spin flip of one ion, and depending on that oscillates in time, with a phase that depends on the wavefront of our laser relative to the position of the ion. Okay, that's what it is. Now, very importantly, because the ions are trapped and we can represent their motion, it's an operator, we can represent it with the bosonic creation and annihilation operators, and therefore we have a time-dependent and Hamiltonian that is also nonlinear in the bosonic operators. And that gives us an opportunity to engineer the interaction between the spins and phonons. So for example, if we illuminate only one spin and we try to couple it to phonons, then we can think of this spin that has an energy splitting omega naught, and we can think of the bosonic mode that has some spacing omega m, that's the ladder of phonons. And by modulating our laser, we can control which transition to drive. For example, if we tune our laser and modulate it at the resonance frequency of this atom, we just realize simple spin flips of the Hamiltonians that are independent of the phonons. If, on the other hand, we tune the frequency to be lowered by the motional frequency, we can realize the James-Cumming Hamiltonian that basically allows an excitation of the spin only if a phonon is absorbed, so the spin and phonon, the flips are flipped. And if we go and shift the frequency by pluses motional frequency, then we can see that an excitation of the spin is accompanied with also emission of a phonon into that mode. Okay, so that gives us some flexibility how we can engineer the spin phonon Hamiltonian. What we typically do is drive many spins simultaneously and also drive simultaneously both the blue and red sideband transition. The reason that we choose to do that is that it allows us to engineer in Hamiltonian here. It has a specific spin operator well defined over the Bloch sphere, for example, sigma x, and also the generator of the displacement operator that we have here with some displacement parameter alpha. And we can visualize the action of this Hamiltonian in the motional phase space. We can write the momentum and position of each of these modes and represent the wave function of the phonons using this shaded area. And what we can see is that if the spin is pointing upwards along x direction, we just shift the wave packet along some direction. If it points downwards, then we shift to the other direction. That's because the displacement is alpha times sigma x. And of course, if the state is in a superposition, then we split the wave function into two separate wave functions, one shifted towards one way and another to the other. Of course, it starts to be more interesting when we drive many spins simultaneously, and by that we get a linear superposition of all the displacement, and therefore the total displacement of the phonon wave packet is a linear superposition of spin operators. Now, in order to generate the interaction, all we need to do is detune a little bit our frequency from the mode spectrum, and that causes the wave packet of the phonons to evolve in phase space. And what happens is, because x and p do not commute, then whenever we parallel transport this wave function along the motional phase space, we accumulate a geometric phase that appends to our quantum state. Okay, and this phase, it corresponds to the area in phase space. In our case, it's a quadratic function of alpha times the number of rounds that we accumulate, and therefore we realize a geometric phase that is a bilinear function of the spin operators. This phase appears here in the exponential, and therefore it corresponds to an evolution by Hamiltonian. In our case, it's the Ising Hamiltonian with our JJ coefficients. Okay, so that's how we can realize these JJ interactions using Treplin spins, basically by accumulating a geometric phase. Now, of course, the participation of ions in different phonon modes, that was for an example for one phonon mode, is known local, and that gives us an opportunity and flexibility in programming the values of the JJ matrix. For example, if we take our 27 ion chain, we can have this mode spectrum that you can see here, if we look closely at one of them. And if we, for example, drive and detune it outside the mode spectrum, we can realize an approximate parallel interaction where you can think of it as this mode, for example, shows the participation is a center of mass mode. All ions move in the same way. The next mode is also a long wavelength mode, and therefore we have a very small exponent that appears here. Whereas if we detune far away from the modes, we can realize a more dipolar interaction. Another possibility is to tune our beams in between the motional modes. Then we have more localized modes of motion, for example, this mode or that mode. And if we sum the contribution over all modes, we find that the interaction is staggered with the order of interaction, and also that it's approximately exponential, and we can control the coefficient of the exponential by detuning closer or further away from these modes. Okay, but the amplitudes that we observe are non-uniform, because you can see that these modes, the participation of the ions is non-uniform. Okay, so we have some flexibility in tuning that. So up until now, we have discussed only the Ising Hamiltonian, which of course by itself is not super exciting, because we still don't have any non-commuting term or something that renders it more quantum. And for that, what we'd like to do is to add some magnetic field. And we can always do a very simple transformation. We can just shift the optical frequency of our laser drive. And by doing that, we asymmetrically move our excitation modulation relative to the red and blue. And that adds a magnetic field. Now, crucially, here the magnetic field is always measured in the frame of reference of the oscillating laser compared to that of the spin. So shifting the optical frequency corresponds in a spin frame of reference to an effective field. magnetic field. This is important because we can tune the frequency of each of our laser beams independently, and therefore have any form of magnetic field here that you would like. It doesn't have to be uniform. So with this capability, let me tell you first how we studied signatures of continuous symmetry breaking phase, which aligns with a little bit of what Norm was telling 20 minutes ago. So maybe the simplest toy model for symmetry breaking in general is just the ferromagnetic Ising interaction that has a Z2 symmetry. It has two different ground states, all spins point up or all spins point down along the X basis. And if we go experimentally and try to measure it, then sometimes there would be a superposition of these states. Sometimes you'll measure the spins up, sometimes down. So the expectation value is expected to be 0, but the correlation is expected to be high. We can think of a generalization or extension of this model that the spin does not have to align along only one axis, but can lie anywhere in the plane. And this is exactly the case of the ground state of this XY Hamiltonian, that as long as the power law is long range enough, and for one-dimensional system, we need this alpha to be less than 3. And then we can realize this continuous symmetry breaking. And the features of this state is that the expectation value is going to be 0, but there will be non-zero correlations for the X or for the Y spins. In order to realize that, we wanted to go and adiabatically ramp the Hamiltonian from a one that is easy to prepare to a funnel one that features the continuous symmetry breaking, provided that we started an eigenstate of the initial Hamiltonian. In our case, we drive the transverse field Ising model with a large B limit in a rotating picture that corresponds approximately to the spin flip Hamiltonian, which is the XY model. And for the initial Hamiltonian, what we applied is a staggered magnetic field Hamiltonian, which you can see here, odd sites and even sites have different sign. Now, typically this would be challenging in an experimental setup because that would require that on the scale of a few microns, the distance between the ions, we would need to alternate the sign of the magnetic field. But owing to the fact that here it's just shifting the optical frequencies of our beam and we have that control, we can absolutely realize that, align with an initial state, and turn this Hamiltonian down and turn this Hamiltonian up. Quite nicely, we also turn on the interactions. Okay, so initially we have no interactions between the spins, and those are ramped up also as a function of time. By doing that, we can study how the correlations evolve in this system. We can take the 27 ion chain and illuminate only, for example, the 7 middle ions. When we do that, only the dynamics of these 7 ions participate in the spin dynamics. All ions move, but only these ions contribute to the spin dynamics. The rest of them, their spin is not coupled because there is no light field that couples them to the phonons, and therefore they do not participate. So it's basically a 7-ion chain. And we can look at the correlation as a function of time, and we find that this correlation builds up, and we can find that all spins become correlated. And then we can extend it, and for the same ion chain, we can illuminate 7, 11, 15, 19, and 23 ions, and we can find positive long-range correlations. And we can quantify this, for example, by taking the continuous symmetry breaking order parameter, that is the average correlation, and seeing that is relatively high as we increase the system size, compared with the average magnetization that is always near 0. There is no preference to align either along X or along the Y-axis. Of course, for this workshop, it's also important to highlight the role of the long-range interaction. This is the approximate form of the interaction that we have realized experimentally. It's not exactly a power law, but it is certainly long-range. And if we compare this to a short-range interaction case and ramp, use the same ramp, we find that the order is much shorter range in contrast to what we measured here. Another thing that we can study is non-equilibrium dynamics. For example, we can initialize our chain in the continuous symmetry breaking phase, and this is, let's say, an arbitrary angle of the spins where they point in the plane. And then what we can do is apply a pi phase shift and basically shift to whatever that is, the other side would point to the other way. That would cause the correlations to be positive within each of these two domains and anti-correlated between the other two domains. And as we let the system evolve under this XY Hamiltonian, we can see that at the boundary the correlations form. They lose the initial anti-correlations, and the system becomes correlated, which means that the transition becomes more smooth between one large domain. So this was a little bit about how we can realize the continuous symmetry breaking phase, which of course is near to the ground state and required us to do some adiabatic ramping. And in order to study some other properties that are finite energy or needs to be outside the ground state, this is a little bit challenging, especially if we have a system where we initialize with some eigenstate and then the gap is very small to nearby eigenstates, and therefore the adiabatic ramping would be much harder to realize. But in contrast, what we do here is a different technique that actually utilizes the fact that these many-body systems can thermalize, and they can do so efficiently. And what we do is we start with product states, and these product states, after thermalization within the system by the interaction of the system, they actually realize approximately finite energy states. And that allows us to then observe and probe different measurements and allow us to construct the observable finite energy systems. Specifically, the system we were interested in is to try to study some phase diagrams of this transverse field Ising model. We all know that for short-range interacting one-dimensional systems, there is no phase transition, but what we do here is we apply a slight modification to this model where we take this coefficient beta and we scale it extensively with the system size. So for L equals 7, we have a short-range interaction, and as we increase the system size, the interaction becomes longer and longer range, although it's exponential. And numerically, we found that there is a phase transition, and we can also then use this technique and prepare different product states, for example, for L equal 13 spins. And then we can observe the dynamics as a function of time and reconstruct, for example, the square magnetization that we have here. And using that, we can construct the phase diagram. Here you can see the squared magnetization that we have for the ferromagnetic case. The bottom axis is the transverse field. The vertical axis is the energy. As we increase the energy, then the ferromagnet melts, and as we increase the transverse field, we can see here the order parameter of the power magnet, and that this one builds up. So that gives an opportunity to probe these, and Alex has a poster exactly on this project, so I encourage you to go and visit him. And so far I've been telling you a little bit about the continuous symmetry breaking phase and finite energy, and now I'm going to share with you some preliminary results that we have in these two different projects. First, I'll start with the signatures of topological edge states. So maybe one of the simplest toy models or simplest models for topological insulators is the SSH model, where we have a nearest neighbor hopping between fermions that have two different type of bonds, either J1 if it's odd bond and J2 if it's an even bond. Okay, and this type of model, it features sublattice symmetry and has two different phases in the ground state. One, a trivial phase if J1 is greater than J2, or a topological phase if J1 is smaller than J2, and the topological phase has localized edge states. Of course, we cannot realize a complete fermionic model. We can realize a spin model, and this is the spin version of this model that doesn't necessarily have to be short range, and we'll discuss what's the role of the long range here and how does it affect the dynamics. But first, we'll start with the short range. How can we realize this SSH model? So in order to do that, we wanted to go for the short range and realize this exponential interaction by tuning near these modes. When we do that, then the spin bonds are very non-uniform. Here you can see a profile of the spin bond that we get if we apply a uniform amplitude spin. So there is a great variation. We, of course, would like to make them at first uniform when there is no diverization, there is no difference between J1 and J2. In order to do that, we just tune the amplitudes of the beams in our array that allows us to correct for the nearest neighbor interaction and make it much more uniform. Then what we'd like to do is to take the Ising interaction, had a large transverse field, so we can realize this spin XY model, the spin flip Hamiltonian. And then in order to induce some dimerization that attenuates even or odd bonds as we wish, we add a time-dependent field that acts like a Floquet field. And this transverse field has this form, as you can see here. It oscillates and has this profile, where the basic idea is that if the field at two sides has the same amplitude, then there is no energy difference in the Floquet frame or in the rotating frame. There is no energy difference, and therefore the bond is not attenuated. But if there is a large magnetic field difference between two different sides, then the bond between these two spins is greatly attenuated. And that realizes the trivial phase. If we shift it by 1 unit of lattice height, we can realize exactly the other state of the that should have a topological state. This is a reconstruction of the interaction in a 12 spin chain. You can see that we made the nearest neighbor bonds relatively uniform. Whenever we apply the Floquet field, then we are able to apply this modulation for the even and odd bonds. And when we have full modulation, we can completely attenuate the different odd bonds in this case. We can also study the dynamics, of course, for this system. So what we do here is that we initialize the edge, and you can see that this is the time, the vertical axis, and this is the site of the spin, and we measure the spin magnetization. You can see that here the spin thermalizes as it propagates throughout the chain. We just see hopping of the spin. Whenever we apply this modulation, then the spin becomes more and more localized until we apply full modulation, where the edge is much more longer lived, and we have no thermalization. We can also study this in longer chains of 22 spins and compare the excitation in the edge to excitation in the bulk. And when we quantitatively compare the late time evolution, what we see is that the edges are much more lived, and every excitation, single excitation that we have in the bulk is thermalizes much more quickly. We've studied many other properties of this model, but in this workshop, I think it's mostly interesting to highlight what's the role of the long range that we have here. And for that, we would like to compare this model to a fermionic model. If we carry these spin transformations for fermions, then we, in fact, realize this type of model we have here is a hopping of the different fermions, where the basically interaction strength is dressed by the occupation number of bonds in between. So if we have any bonds, if the interaction is short range, then these two match, the spin and the fermionic case match. But if interaction is not short range, then what we find is that any bonds in between, there is a dependence on the occupation number, and this is the interaction terms. In order to study this, we need to go to states that do not have just single spin excitation, but have many more excitations. That's exactly what we do. We start our system in the nil state, and we see how the spins thermalize very quickly. When we apply the Floquet field, we see that the thermalization slows down, and the edges become much more localized, and this is for a much longer range interaction. It's a different interaction matrix that we have programmed. And when we compare it to theory, we find very good agreement. But most interestingly, if we take, for example, the middle case of moderate simulation, and we take our data and compare it to this exact model, or compare it to a free fermionic but long-range model, we see that there is quite a discrepancy, which shows that the interaction terms are important in telling the story of what's going on here. And this gives an opportunity to study how these interaction terms, for example, can oppose the topological protection that this system has. And finally, so I told you about these three projects. Let me finally tell you about our last project, about string breaking dynamics. Here we consider a different model where we have the spins here that are subject to this Hamiltonian. We have, as before, long-range Ising interaction. We have transverse field, but we also have now longitudinal field that could also be side-dependent. And this longitudinal field, for example, in this case, can make those spins to pin them to their space, so they cannot rotate. So these spins are frozen, and they can act as boundaries for the string that we have here in the middle. And we can ask ourselves, how does the confinement of this string looks like? When would it break? And so forth. And if we look into a diagram that shows the transverse field and the longitudinal field, then this system has a first-order phase transition where when the string breaks as we increase this longitudinal field, and of course it melts as we increase the transverse field. Okay. Now, experimentally, in order to study this model, this means that we need to apply this longitudinal field to the ion spins that we have here, and typically this would be quite challenging. So in order to do that, what we apply experimentally is that we prepare a second array of individually controlled laser beams that we can independently control their frequency and amplitude. So we prepare the first array, we change the amplitude so that we can engineer the Ising interactions to be uniform, and then we can also shift the frequency of the different spins. And the second array, we tune it to be near the carrier transition when we drive the spin flips without having the coupling to phonons. So that's basically just a longitudinal field. And we control the different amplitude of the different beams in order to construct the model that we're interested in and simulate the dynamics. Quite nicely, we need also to stabilize the optical phase between these two arrays, because otherwise that would cause this field to drift in time, and we do so quite efficiently. And that allows us to study this dynamics. And here I can show you one example. When we take, for example, our initial string where the spins point downwards and we have a weak wedge below the transition, what we find experimentally is that the string maintains its magnetization. Again, here we have time, here we have sites of the spins, and we can see that the spin, there are some coherent oscillations, but we see, we can see that the string maintains its magnetization, it is measured. On the other hand, if we have a larger quench, then we find that the spring starts to break, and we find much larger magnetization here with great agreement with our theory. Okay, so let me summarize what I've told you a little bit today. I was discussing the how trapped ion quantum simulators work and what's our ability to program them, what are the different knobs that we have to control the model. In principle, these are the family of models that we know how to realize. We know how to realize the Ising interaction. We can ramp the coefficient as a function of time. We have great control in tuning these different matrix elements to be short or long range. And we can also apply time-dependent transverse and longitudinal fields that also vary at different sites. And that gives flexibility to simulate different models, continuous symmetry breaking, topological edge states, or variations of the SSH model, string breaking dynamics, and also to probe probabilities at finite energies. With that, I'd like to thank you for your attention, and also thank all the theory collaborators that we have on the different projects. Alexi, Mohammed, and Jushwan on the continuous symmetry breaking project, Diego Porras for the SSH project, Alexi and Mohammed for the finite energy project, and Zoe and Alexi for the string breaking, and all the postdocs that we work with, Alex, Alessio, Braden, Eleanor, and Federica. And also, as a last slide, just to advertise that I'm going to start a position at Cornell, and if you're interested to read more about it, then feel free to reach out. Thank you.
Yeah, I had two questions. One is, you had this image in the very beginning of your trap. Can you, like, of your 1D trap, the very first one, early one? Sorry.
Yeah.
Yeah, maybe the next slide.
This one?
Yeah, so I'm wondering whether, it's maybe trivial, but like, is the axis of the trap, principal axis of the trap along the rectangle or along the ions? Or are they just placed sideways a little bit because of Coulomb interaction?
Oh, so we apply usually a confining potential in the radial direction.
Right.
Okay, which is very strongly confining. Then we apply a very loosely confining potential in one dimension along one line, and then they form the crystal along this line.
I see. They don't like climb off the walls a little bit to be further.
That's a good question. We do experimentally. Yeah, so we do experimentally at very long chains, observe a little bit of tilt. But what we do is that we have these cheap traps that we have all of these different electrodes. We have 100 electrodes here, and we can tune the different voltages so we exactly compensate for it.
I mean,
and
I'm just
we control that.
The image, is that real? Like, it looks like the axis of the.
Oh, that's just because the camera is tilted.
Oh, okay.
Rotated, sorry.
Okay. Sorry, and then the maybe more technical question is, so you focused on linear terms coming from the cosine, interaction of laser with the spins, but is there a regime where can you have the high order terms important, nonlinearity?
Yes, absolutely. So we came up with some schemes how we can actually utilize the second order, for example, and use that. So we use a second order of the bosonic interaction. So we drive the second sideband transitions, and with some specific reconstruction, this gives the opportunity to engineer any n-body interactions between the spins. Okay, so even though it's just second order in the bosonic, it gives you up to n order for spins, up to the length of the chain, and we definitely have schemes that we use that. Less for quantum simulation, but more in the context of quantum computing. And the reason for that is that we need to drive very strongly the phonon modes, okay, at least in this setup, and I'll explain why. We need to drive very strongly the phonon modes, and usually for these quantum simulations, we want the Hamiltonian to be additive, so we can add more and more terms. So we'd like the coupling to the phonons to be in the dispersive regime and very weak. Okay. Specifically, what controls whether these terms are important or not is a parameter known as the Lambdicki parameter, which is the extent of the wave function of the ion compared to the wavelength of the laser, basically, or the effective driving laser.
Super nice talk. One quick question. So in the symmetry breaking part, you were focusing on sort of alpha less than 3. And if I'm sort of recalling correctly, alpha less than 3 gives you ground state order. But I think, if I'm recalling correctly, alpha less than 2 in principle gives you finite temperature order. Is that something that you guys can explore or have explored, and how does that change things?
So yeah, let me go to this slide. So
a lot of slides to go through.
Yeah. Nearly there. So if we look into the interaction that we have for our 27 ion chain, and you see that this is on a log scale, log scale, and you see this is not linear, right? So it's not exactly a power law. It's actually, we feed it to a power law times some exponential decay. But this exponential, it also scales as you scale the system. This coefficient scales, so it can still be long range. But it's not exactly a power law, at least for this system. We can engineer it to be more and more power law if we change the trapping potential. So this is definitely a possibility, and in principle can be done, but it's not true for the specific crystal that we have formed. But it is long range in that sense.
Why does it fluctuate much for small distances?
Here?
Yeah.
Oh, so here we have experimental data and theory. So you see the fluctuations are the experiment, and the theory is here, and it's a relatively good match. The fact that it doesn't match to the theory could also be that things drift or things are not exactly. So almost all of the theory that we have shown is with no fitting parameters to the specific experiment. It's just we tune things experimentally to what we expect from theory, and we apply and we compare. So if things are incorrect or not properly calibrated, they would respond to these changes.
So is there any kind of limitation on the scalability in terms of the alpha that you can engineer? So for example, like here you're showing the potential that you get for, a particular system size. How does actually, what are the resources required to engineer the same alpha, at, double the system size, is that something relevant?
Yeah, that's a very good question. So in principle, if the more control we add to our lasers, the better we can engineer this JJ. And if you have a number of control knobs that scales quadratically with the number of ions, you can tune every element in the JJ matrix, okay? That's basically what it is. And we can do that, but it requires a lot of control and a lot of calibration. So usually the form of interaction that we practically realize is the one that are the easiest to realize. By changing the different trapping potential, usually you can take and change some scenario or one configuration that is hard to realize or requires more control to one that requires less control. But it always goes down the question, how much control do you need to engineer this interaction? So to answer your question, yes, it's possible to do that, but experimentally it's more challenging.
Yeah, so for the SSH experiment, have you tried to prepare the ground state of this Hamiltonian? Because it looks like you are just doing some quench dynamics there.
Correct. No, we have not tried to prepare the ground state Hamiltonian.
Is it just like too challenging, or you need more ramping time?
So we just wanted to study, I think, the role of the long-range interactions. We prepared different configurations of the, I showed one of them, but we prepared several configurations and we studied how the long range affects the system. We thought that this is just interesting, but we have not explored the ground state preparation.
Hi, yeah, thanks for the cool talk here.
Oh, thank you.
Just have a question about the SSH part. So once you add long-range interactions, don't you break sublattice symmetry immediately?
Yeah, that's a good question. The form of the pattern that we have actually maintains the inversion symmetry throughout the lattice, even though it's long range. So yeah, so the way that these bonds are attenuated is that we have here, for example, an attenuation for the nearest neighbor bonds. Here we have attenuation for the next nearest neighbor bonds, but we do not have attenuation for the third and for the fourth. And then we have attenuation for the fifth and sixth, and we don't have. We have and that's a system to be. This specific reconstruction maintains the inversion symmetry even though it's long range.
Hi, thanks for the nice talk. So I have two questions. One is related to the thermal states. So how are you sure that the system respects ETH, even if, you know, a long-range system, sometimes you have pre-thermalization in certain, parameter regime? And the second is more technical. You said you have an additional array to create this longitudinal field in the string breaking. Isn't this just, and it's challenging to stabilize the phase, isn't this just like an additional tone on the carrier, or it's actually another set of physical beam?
Yeah, so for the ETH part, I think that basically, I mean, I don't argue that we prove here that it works. I can say that we compare it to the numerics that take into account the dynamics, and we find a good match. And they are compared to what the ATH predicts. For the experimental part, both things you said are true. We apply a different tone, which means that we take our acousto-optic modulators and add another frequency to it. But because the AOM, the way that it works is that you get a different deflection angle, so you actually get a different array of beams. They propagate through the system, okay, a different array of beam, and then we focus them to the system. So they are generated by what you said, but it's a different array of beams.
And maybe a follow-up, how do you stabilize the phase? You said that you have to stabilize the phase.
So we have many different, I think it's mostly the system engineering that is very well engineered, such that we can...
so it's passive stability.
So that it's passive. We have also active stabilization layer of the entire setup, and so it's not just passive, but I'd say we have stabilization for the system, for the optical pathway, of course, and we do calibrate these phases very routinely. So the drift is long in time, okay? It's slow, and we can calibrate that very efficiently and consider this when we run these experiments.
Thanks.
Great. So if there are no further questions, well.